Hello, and welcome to the Burns & McDonnell Jackrabbit Substation Senior Design Project, a project made up of 4 electrical engineering students and advised by Dr. Timothy Hansen. During this presentation, we will be going over the physical design of our substation, the grounding protection, lightning protection, and then backup DC and AC storage for providing power to the substation.
Today I'll be talking about the physical design and the grounding grid for the Jackrabbit substation. On the upper level, the purpose of a substation is to either step up voltage or step down voltage. For specifications that will be fulfilled by our physical design, we have substation will need to be expandable into 6 line positions and only 2 breakers required to isolate a local fault. So this is our yard layout. Currently it's a ring bus configuration with 3 line exits. It's called a ring bus because the bus work is in the shape of a ring. It is expandable. So at the bottom of the picture, you can see a future expansion bay written. If you would install breakers down there and line exits, you could get up to 6 line exits on our substation. And that would also change the configuration from a ring bus to a breaker and a half. The breaker and a half configuration is a lot more flexible than a ring bus in the sense that it's a lot more reliable. And we only need 2 breakers to isolate a fault. And if 2 breakers open, we won't have any other lines being affected. So using this layout, we can fulfill our 2 specifications. Along with that, in the middle of our current ring bus, there is a drive path that is wide enough for a vehicle to drive through. So if anyone needs to service any equipment, they will be able to drive a vehicle through that section. This is our cable trench. It's going to run from our control house to any equipment that needs communications. So that would be transformers and breakers and things like that. That's for SCADA use, so supervisory control and data acquisition. That would allow us to open breakers remotely in case of faults or close breakers remotely in case of faults. We are trying to minimize the total length of our cable trench. We do that by running it out of the control house, down the side of the transformer and into the middle of the ring bus. This minimizes the total length of our trench while maximizing how much equipment we can get to. So this is a 3D render of our substation yard. You can see the blue cable trench, the dark blue cable trench, the light blue grounding grid, and then all of our major equipment and the likes. The bus work is 7 feet apart. This was chosen because 7 feet will stop any voltage from arcing from line to line, thus ensuring safety in the substation. Finally, for physical layout, we have our control building layout. This includes batteries from the DC study in the top middle, and it houses all the controls equipment for the substation. So we have our relay and communication panels, our DC load center, AC load center, and automatic control switch. Finally, we have 2 doors in our control house. This is just to ensure that people can get out safely in case of emergency. Next, we're going to talk about the grounding grid. The purpose of a grounding grid is to ensure safety in substations during fault conditions. Our grounding grid was designed to IEEE standard 80-2013. For specifications, we want to limit the touch and step potential below safe limits. So we're just going to hit a few quick definitions. Touch potential is going to be the difference in potential between equipment and the person's feet when they're working on it, so when they're touching it. While step potential will be the difference in potential between a person's feet when they're walking. Obviously, we don't want the path of least resistance to be through someone's body because that would not be good for our substation. That would not be safe for our design. So using this soil resistivity chart, it was determined that the maximum grid size would be 30-foot squares. However, we chose a more conservative 25-foot square grid. This allows us more flexibility in moving the grounding grid, either shifting it left and right around foundations. Along with that, it gives us more safety in the substation. So here is our grounding grid, our preliminary design at least. The grid expands past the edge of the fence in every direction. That's to get fault current away from the equipment as quickly as possible. The purple dots are grounding rods, which are 20-foot rods pounded vertically into the ground. Their purpose is to get fault current as deep into the earth as quickly as possible. The reason behind that is the deeper you go into the earth, the less resistive the soil gets as it's moist. So that will help us to dissipate fault currents faster. So Our grounding grid was simulated by our sponsor, Burns McDonnell, in a program called CDIGS. We were not able to simulate this ourselves, as a single key of CDIGS costs $20,000, but our sponsor still wanted us to get the experience of seeing what a simulated grounding grid looks like. So the picture we're looking at is the step potential for our grounding grid. The maximum allowable step potential is 2,220 volts. Our grounding grid, at a worst case, hit 407.8 volts. This was only around the edges of the substation, the corners. This is a problem with the software because the software cannot simulate an infinite plane or a semi-infinite plane like the Earth is. So the area where two lines come together, where there's nowhere else for current to go, are going to have higher voltage levels. And we kind of see the same thing in the corner with touch potential, where the corners have a significantly higher voltage level than everything else. For touch potential, the maximum allowable is 672 volts. The maximum simulated is 481.27. Like I said, there's higher voltages on the legend, but the area that we care about, where most of our equipment is located in the middle of the substation, is primarily yellow or below a touch potential of 81.1 volts, which is well within the safe limits.
Hi, my name is David Sikora, and I will be going over our lightning protection. So the purpose of our lightning protection was to provide protection against any electrical surge that our substation might experience. Some specifications we had to follow. We had to follow the IEEE standard for direct stroke lightning protection for substations. We had to use the fixed angle design method because this was what our sponsors were most familiar with. The failure rate was to be 0.1% or less, and the maximum mast height was 66 feet and 2 inches as designated by our sponsor. So to start out our design, we had to finish our layout for the substation first, and then we could kind of build off that. So our initial design of the substation had 6 lightning masts, and that's going to be 2 on each of the exits, as you can see here, here, and here. So then we just added masts until all the equipment was enclosed. So the protection that the mast would offer depended on the height of the equipment, and it also depended on whether the circle of protection that the mast offered was overlapping versus non-overlapping with another mast's circle of protection. So if they weren't overlapping, they offered more protection because IEEE found that it was more likely that lightning was going to strike that higher mast than it was to strike anything between those masts. So then we just kind of kept adding masts to our design until everything was enclosed, and you can see our final protection there on the right. It has a total of 9 lightning masts. So then, as a way to kind of judge how well we protected our substation, we did some calculations to determine the time of failure. So no protection can be 100% effective. You can keep adding masts until you've got as many as you want, really, but it's never going to get the protection up to 100%. So you can see how we calculated our failure rate on the right. First, we determined the number of lightning strokes that would get to the ground per year for the Brookings area. Then we used that number to determine how many of those flashes would be within the area of our substation. And then we used that number and we multiplied it by our desired failure rate, and we had a failure rate where 1 lightning stroke would get through every 32,000 years or so. So we wanted it to be 0.1% chance of failure. We actually had 0.003% chance of failure.
Hi, my name is Noah Anderson, and I'll be going over the DC battery study. So the purpose of the DC battery study was to design a lead-acid DC battery bank to provide power to the substation in the case that it's lost. It must provide power to all of the DC substation loads and be able to work in a worst-case tripping scenario, all while following IEEE standard 485-2010. Some specifications for the battery bank is that it has to be a lead-acid battery. The battery must also be able to provide 8 hours of power in a worst-case scenario and be able to recharge within 8 to 24 hours. This worst-case scenario that we're talking about is going to be a fault on the transformer, which would cause breakers 1, 2, and 4 to trip, which would need power to be able to trip. The battery needs to be able to hold a steady state battery load, so it can't be drained to zero, otherwise that'll damage the battery. It must also be able to provide power to our relay and metering loads, as well as SCADA communication and operation of the motor-operated air brake switch. For the load classification, it's broken up into 3 different groups. Our first-minute loads, which you can see on the right, is just the operation of the 3 breakers. Our continuous loads, which involve relaying, metering, the RTU, steady state load, and other things like that. You can see the total amperage added up on the right. And our momentary loads, which could happen at any point in our battery's duty cycle, which for this case, it would include MOAB operation and the trip coils. For our total amp hour calculation, we had to take into consideration 3 different battery correction factors of temperature, age, and design margin. These were decided to be 15%, 25%, and 10% respectively. Our total amp hours after those correction factors came out to be 178.126 amp hours. Here you can see our battery's duty cycle. This was helpful for calculating the battery charger sizing. So it's split into 3 blocks of our first minute, continuous, and momentary loads. And so for our battery charger design, we used this equation here to find our amperage rating of the battery charger. Using the numbers given, we're able to find a battery charger size of 13.16 amps. However, this is not a standard battery charger size, so we had to increase it to the next closest standard battery charger size, which was 16 amps. Plugging this number into the time section of the equation, we were able to find that our charging time was 17.8 hours. Now, to select a battery meeting all of the criteria that we've talked about previously throughout this, we decided on 20 power-safe 3CA-7M batteries. This bank would give us 153 amps of single-minute capacity, greater than the 144 amps from our duty cycle. It's also rated for 17.7 amps of power for 8 straight hours, which is also greater than what we showed in our duty cycle. They have a 20-year life expectancy and are able to reach a full charge in 17.8 hours.
Hello, my name is Tyler Jorgensen, and I will be discussing the AC system sizing study for the Jackrabbit substation. The Burns and McDonnell senior design team completed the AC system sizing study during the spring semester with support from the 3 engineers at the Kansas City Burns and McDonnell office. The purpose of this study was to properly size station service voltage transformers, SSVTs, which are line to ground single-phase transformers that step down high voltages to a usable level to supply AC loads. The specification was that each SSVT had the ability to supply more than 100% of the worst case expected loading while maintaining redundant protection if a set were to trip offline due to fault conditions or internal failure. The Jackrabbit substation design team compiled a list of major AC consuming loads to properly size the primary and backup SSVTs for all expected loads. Diversity factors, which are a measure of how often the load will be expected to run, were considered for the seasons of winter and summer, since the substation is located in the harsh environment of South Dakota, which can swing over 130 degrees Fahrenheit in a calendar year. Loads such as transformer fans have a diversity factor of 1 in the summer to maintain operating temperature, but is reduced to a factor of 0 in the winter when sub-zero days are common. A table was compiled that listed out 17 major AC loads that were considered, as shown on the table on the right, that considered the equipment, quantity, diversity factor, and the resulting demand. The top 5 loads that affected the total substation demand included circuit breaker heaters, roof vent fans, HVAC, yard floodlights, and the 125-volt DC battery charger that was selected in conjunction with the DC battery study to charge at the recommended rate. These loads ranged from 13.7 to 3.8 kVA, respectively. Each load was given an assumption or link to actual equipment as a quality control check to verify realistic values. While the loading was similar between the seasons of summer and winter, it was determined that under the worst case loading conditions, the summer would be the limiting factor at 29.1 kVA. Therefore, each SSVT is recommended to be rated for 35 kVA. This was selected to guarantee the substation would still be operational if all loads were connected to a single phase. If this were the case, these loads would account for 83.3% of maximum capacity of the SSVT. With the overall specification that the substation can be easily expanded into future line positions, this accounted for future loads and would still provide additional loading without the need for new SSVTs to be installed during the next phase of the project. The controls design consisted of electrical wiring for AC and DC elements. The AC schematics, which include the one line with relaying and line differentials, show the interactions between equipment CTs and yard CCVTs into the overall protection scheme, while the DC schematics show interactions between the defined relays, lockouts, and the breakers trip coils. The first deliverable of the spring semester's control design was the one line with relaying, as shown here. This schematic is base for every following schematic, as it outlines each device with its ANSI classification based on how the relays would be configured. This universally communicates what function our substation is capable of and the level of redundant protection throughout the substation and on the Watertown and Sioux Falls line exits. AC line differential schematics will show the protection scheme surrounding the breakers and the transformer, while providing a wiring level view of each relay. Major inputs and outputs are wired to show mutual interactions. DC breaker schematics show the individual protection devices associated with each breaker and the transformer. These show what can trip and reclose. If operation or failure occurs, alarms and lights were wired to alert system operators throughout the annunciator. Transformers are the most expensive pieces of equipment in a substation, therefore they warrant the most protection. The DC transformer schematic shows all equipped relays associated with the zone of protection. The tripping table included on this document interacts with every breaker besides one in the yard. This was the last deliverable, and it referenced every major spring print in some form. While we did not have the liberty of choosing the relays for the overall protection scheme, we gained valuable experience and understanding on how relays monitor and report system conditions while ready to react to a failure or fault in the matter of seconds. Each system is distinct and interconnected as part of a layered protection behind the scenes. In conclusion, the project objectives were completed per the request of Burns & McDonnell, the provided scope of services document, and the SDSU College of Engineering. All studies performed followed the proper IEEE standards to ensure the safety and reliability of the overall substation's design. The lightning protection was found to have a penetrating stroke every 32,238 years, or 0.003% chance that lightning will strike yard equipment. The grounding study had both simulated touch and step potentials below the maximum allowable voltage. The fall semester physical layout achieved a space-efficient layout that was configurable to future expansion. The DC batteries are able to operate for the minimum 8 hours if power is lost to the substation, and all AC substation loads can be serviced at any time of the year with redundant protection built in. And that is the project, Burns & McDonnell, Jackrabbit Substation. Thank you.